Hello and welcome to another rendition of Algebra 2. So here we are at 4.5. And I'm not going to lie, I've been avoiding this video for a minute because it's synthetic division. I've never been that great at synthetic division, or at least not a fan of it. But it is a valuable tool, and you are going to at least use it in pre-calc and probably more so in college. So here we go. I can divide polynomials using both long division and synthetic division. So our spark, our activity, or whatever, spark your learning. So this is the Van de Graaff generator. It produces static electricity. And according to this little graphic right here, our Van de Graaff has a current of I and a power of P. The voltage is found by using the current and power. And yes, it does make your hair stand up. So, what mathematical questions, do we have a specific equation for the current and power? Can we find an equation for the voltage? And turns out, of course, there are equations. So they give us, let's zoom in here. So they give us our current. Current is traditionally uses I, so that's a function I of t. And then they gave us power. Now, how they determine power, current you can figure out from, there's meters that'll tell you current. I don't know how they figured out power, but hey, it's all based on t, which is time, which kind of makes sense because the longer you hold your hand on this thing, the more you get electrified, and then the more current, more power you're going to have. So the voltage is right here, is P divided by I, or power divided by current. And so by dividing those two functions, you can come up with the simplest version of voltage, which voltage is a useful thing to talk about of like, how dangerous is it going to be? So usually voltage and current are the two things that you want to know if you want to know if some version of electricity is safe. So that might be what they're looking for. So let's jump into it and figure out how to kind of do some of this stuff. All right, so our first task in dividing polynomials. We're going to evaluate a polynomial function using synthetic substitution. So it's going to look very closely, are very similar and act very similar to synthetic division, but this is using the tool of synthetic division to evaluate a function. So that would be like you have an f of x and then x equals 4. What is the function going to equal at x equals 4? So the one way to do it, and I'm not sure, I guess they would use this nested form when maybe you didn't have a calculator or something like that. So typically, if you're going to evaluate a function, you would just take something like this, and if you had f of x, so if it turned into f of 4, you would just plug 4 into all of these x's, and then you would evaluate the function. Let's say you didn't have a calculator and you had to do it by hand. That's where this nested form comes in. I don't think I would ever use the nested form, but here it is. And what they're talking about, like evaluation steps down here, you would first evaluate this inner part and making sure that you're paying attention to rules of priority. I forgot the name of them at the top of my head, but remember, you always multiply first, and then you do everything in parentheses. So you're going to multiply this first, and you're going to add b, then you're going to have a number for this, and again you're going to multiply it by the x, and then you're going to add the c, and then you will have a blue number. And hopefully you're picking up on the pattern. You're going to multiply by x, add d, so on and so forth. So that's one way that you can take this function and evaluate using a nested form. Again, I'm not sure why you would ever want to use a nested form, but there it is. So we're going to evaluate a polynomial, p of x, for a specific value of x, can also be accomplished by using synthetic substitution. So again, it's going to look a lot like synthetic division. It's going to act like synthetic division, but we are going to be evaluating a function for a specific value of x. So let's check it out. So let's see if I can find some white space so I can write. So the nested form of p of x, all of that, is this. Notice that p of x lacks a linear term, which must still be accounted for in the nested term. So let's see here. Put the operations performed when evaluating the nested form of the polynomial in order. So, okay, we're not using synthetic division. They're going to make a comparison here. So we're doing this nested form first. So I'm going to go ahead and write that down because I'm going to forget it. Because I forget most things. 2x plus 5 minus 2 plus 0 minus 8. And where'd my eraser go? There we go. All right, so if we were to evaluate at p equals p of negative 3, that means that our x value is negative 3. So again, let's say we have these high order degrees. I mean, I can still find negative 3 to the fourth, but hey, whatever. You can also use the nested form. So the first thing you're going to do is you're going to do the multiply. Oops, I accidentally erased it. You're going to multiply and then add. So you're going to multiply first and then add. Oh my gosh. So we will multiply by 2, multiply 2 by negative 3. Remember, our x is negative 3. So then after that, we're going to our 5. So then we're going to add 5. Add 5. So then we have this number. So the next thing we're going to do is we're going to multiply by x, because multiply comes before adding or subtracting. So we're going to multiply by x. They don't have that, so we'll just, I guess it's assumed. So then after that, we're going to subtract or add a negative 2. So now we have this taken care of. So then again, we times by x, we add 0. I doubt they're going to have us write that, but oh, look. Just for fun, add 0. That is this 0 right there. So now we have this number. And so now we are going to subtract 8 or add a negative 8. Oh, you know what we forgot? I assumed that was multiplying by x, but we got to add these multiply by x a whole bunch of times in there. So that's going to go in between every single one. So I think this one's going to go here. Now that one will go at the end. I love these programs. Multiply 2 by negative 3 plus 5. Then we're going to multiply by negative 3, add negative 2, multiply by negative 3, add 0, multiply by negative 3, and add the 8. And notice how the 8 is outside of the parentheses, so we're done multiplying by 3. Woo! Thank goodness, right? Okay, get out of here, nested equation. Oh, I didn't actually do the math. Again, I didn't do the math, so whatever. So I'm skipping that because I want to actually spend more time on consider the synthetic substitution array for this is the exact same polynomial at negative 3. So how are the numbers in the top row of the array related to p of x? Select all that apply. So here is how we would set this up. So hopefully some of this looks familiar. So you've got your negative 3 here. That's what we're evaluating at. And you've got your coefficients going from left to right in standard form. 2, 5, negative 2, 0. Note that there is no 0 in here, but this is your x to the first factor. So even if you're missing an x, you still have to add that 0 in synthetic division. Even in long division, I think you still have to do that. And then negative 8. So that's where they got these numbers. And the rest of this, again, should seem very familiar. You're going to take 2, drop it down. You're going to take 2 times negative 3. That's where you get the 6. The negative 6. You're going to add with the blue arrow. Get our negative 1. Then you're going to take negative 1 times negative 3. That's where that guy comes from. You're going to add going down. So then you're going to have this 1. Again, 1 times negative 3. That's where this number comes from. So 0 minus 3, negative 3. So then negative 3 times negative 3. You're going to have 9. And then negative 8 plus 9 is 1. So the answer is for p of negative 3 is your final number here. So we can come back up here since we did synthetic division. Try again. 1. Yay! I cheated. So that's how our synthetic division works in this situation. So again, synthetic division is a valuable tool, and should be practiced, but you need to make sure that you are using that tool for the right things. For example, you don't want to try to hammer in a screw, you want to use a screwdriver. In this situation, synthetic division or synthetic substitution works really well. So let's see here, see which one of these are correct. The numbers come from the degrees of each term. They're the coefficients. Okay, so this next one, the numbers are the coefficients of each term of p of x in descending order by degree. The numbers include a 0 because there is no linear term with x to the first power. I'll agree to that. The numbers are the 4 individual terms of p of x evaluated when each is evaluated for, maybe? Yeah, I didn't think so. That made it sound like you were evaluating them first when you put it in this top row. So that didn't sound right. So let's see here. What number in the array tells you the value of p of negative 3? So we already talked that it's that one right there. And then you are good to go. How does a framework in synthetic substitution array show the sequence of multiplications and additions used to evaluate the nested polynomial? So it follows the same pattern as our nested polynomial. That's why we did that up here at first. So if you look at it, 2 times negative 3, we did that in our synthetic division. Then we added 5 times by negative 3, negative 2. So we followed this same pattern here. when we went through synthetic division. So that's the point that they're making, is that synthetic division is really just using this nested form. This thing right here. So it's kind of, why does synthetic substitution work? It's because of this right here. We're just kind of, I don't want to say dropping, but we know that we have the variables there, so let's just get the math done and then put the variables back in. So there you go. So our task 2, again, we're dividing polynomials. Divide polynomials using long division. Yes! I love long division. I don't like synthetic division, but I love long division. So before we get started, when you're doing long division, remember, here's our little vocabulary terms. You will, for the book or for this program, you have to express your answers in quotients plus the remainder over the divisor. So this is good to kind of take note. You have a fraction or a divided by situation. You have your dividend on top, your divisor on bottom. Let's just zoom in. And then you will have your quotient, which is the answer you get, and then the remainder. I would say if there is a remainder, but a lot of these problems are going to have remainders, so kind of sort of get used to it. So in our example over here, we have our dividend, we have our divisor, and then when we do that math, we get our quotient plus our remainder. Well, actually, I should rephrase that. Our remainder over the divisor. So that's going to come into play a little bit later, especially after you've worked on problems and you enter it in and then you get it wrong. It's probably because it's not in this format, which can be frustrating, but deal with it. So let's see here. Multiply each term by the divisor yields a dividend. So we already talked about that. All right, here we go. Use long division to find the quotient and remainder of that stuff. So first we want to write the problem in long division form, or whatever you want to call it. So the dividend and the divisor in standard form include a coefficient of 0 for any missing consecutive terms. So just like in synthetic division, it's important in long division to include those zeros. So the process for this long division is going to be very similar to normal long division. It's just now we have variables. So we need to figure out how many times this goes into this. And we'll start off with looking at our first x squared term. And then this is going to be an x cubed term. So, okay, what are we going to have to multiply to get to that? It's going to be another x, right? So in x times this is going to be our x squared. So that's going to go right here. We're going to zoom in. So there's our x. And then we'll need a coefficient. So again, how many times does this go into this? 2x times. So it's going to go in 2x times. So once we have that, so now we just take this number multiplied by all of this. So just so you can see it, this number multiplied by all of this, and you're going to put it right underneath. So 2x times x squared is going to be 2x cubed plus 10x squared, and look at that, it lines up, plus x. Now remember, in regular division, you would then subtract this, so there's going to be a negative, negative, and negative, and you're going to add those, or you're going to subtract them together or add the opposite. So these cross out. So 4 minus 10 is negative 6x squared minus x. So then you're going to bring this guy down, minus 2. So now you're going to do the same thing over again. So we've got negative 6x squared. We've got an x squared here. So I would say negative 6. Negative 6. So now we're going to multiply our negative 6 by, see, I already messed up the words. By the dividend. Divisor. See? Vocabulary is not my strong suit. So multiply the negative 6 by the divisor, and we're going to put that all down here. So negative 6 times x squared is negative 6x squared. Minus 6 times 5 is negative 30x, right? Yeah. And then minus 6. So again, we're going to subtract that or add the opposite. So then you just add them all up. So cancels out. There's the bell. 29x and plus 4. So we're out of terms here. So normally this would be your remainder, right? Well, it still is our remainder, but the way we're going to write our answer is in that weird format that they gave us. So typically, my brain just goes, cool, so the answer is 2x minus 6 plus the remainder, which is 29x plus 4 over x squared plus 5x plus 1, right? So it's just the remainder that doesn't divide equally into it. So that's not what they're looking for. So what they want their answer to be is they want your answer, well, actually, let's do it in the right order. So they want the divisor, so that's this part, x squared plus 5x plus 1 times your answer, 2x minus 6, plus the remainder. So you can remember that in any way you want. You can either go just straight up remember that's how your answer should look, or I don't know why my brain likes it better, but my brain looks at this and goes, okay, let's get rid of the fraction. Let's times this entire thing by the divisor so that we don't have a fraction, and then that's what we get right here. So there it is, and there's our remainder. However you want to remember it, it works. So let's see here. I'm sure the book has all this stuff for us. Yeah, so it's going to go through each step. So the term 0x is a placeholder. It appears in the dividend to indicate that there is no x term. Cool. So again, step by step, 2x, you're going to times it by the divisor. There it is. You're going to subtract it out. Then you're going to get your 1 right there. Negative 6. And then, so again, write the result in the form dividend equals divisor times quotient plus remainder. So that's what we were talking about right there. So here's our divisor, here's our quotient or our answer, and here's our remainder. And this is just the only thing that was left that we haven't played with yet. So all of these, you can always verify your answer, and that is just multiply this all the way out and make sure that you get this right there. So this is what they do right here, is they multiply everything out, and they do in fact get the same equation on both sides, therefore it is equal. So not terrible, right? All right, task 3. We're still dividing polynomials. This time, divide p of x by x minus a using synthetic division. So the last problem we used long division. This time we're going to use synthetic division. So there's a couple things we got to go over real quick. So the last row of synthetic substitution array gives the coefficient of the quotient and the remainder. The remainder of the value of the polynomial for the value of a in ax minus a. So we'll make sense of that in a minute. So the remainder theorem, when p of x is divided by x minus a, the remainder is p of a. So that's going to be a number. Anyway, so we can use synthetic division to divide polynomials similarly how you would regular numbers. So this is our example of long division, and here's our example of synthetic division. So I mentioned at the beginning of this that I was a little worried about synthetic division, but you can see that there's clear advantages. It takes up a lot less space, and once you get good at it, it is much faster. So the way this is going to work, so the divisor, which is this number right here, I say number, this function, x plus 3. So the first thing you need are the zeros for that function. So if you took x plus 3 equals 0, what is x going to equal? X is going to equal negative 3. So that's kind of what they did up here. So we are going to use negative 3 for our synthetic division. So that's where this number comes from. And then as we go through, I'm even going to match their colors, look. You're just pulling the coefficients out of the actual function. So did they, let's see here, did they list the function anywhere? All right, guess not. So they're using this function right here, which is the same one as, I think it's the same one as before, but either way. So we're just going to go along. We're going to take those coefficients, and it is in standard form, so that is important for synthetic division, but you've got your 2. Notice that you have your 0. Same thing for both ways. It is a placeholder, and then you've got your 4 and your 5 coming from 4x and then 5. So then it's just going to be your normal synthetic division steps. So bring this number down, multiply that number, so you get negative 6x, add, so there you go, you got your 6x, negative 6x, sorry, so on and so forth. So negative 6 times negative 3, positive 18, add it together, 22, 22 times negative 3, negative 66, add it together, you get negative 61. So you've got these numbers down here. What do they mean? So this last one right here is your remainder. So you can, and this is the part that you just have to remember. So this is your remainder. Your remainder is going to be negative 61 over x plus 3. And then here is your answer, if you will. So that's going to be 2x squared minus 6x plus 22. And you can do it backwards. So you've got your x to the 0th term, or just your regular number, your x term, and then your x squared term. So our answer ends up being, let me write it a little bit nicer, 2x squared minus 6x plus 22 minus the remainder, which is 61 over x plus 3. So just like the last time, that's not how you're going to enter it in. You're going to enter it in as the quotient times the divisor minus plus or minus the remainder. So, or like I like to think about it, get rid of this fraction. So we're going to times everything by the denominator right there. So that's going to end up being 2x squared minus 6x plus 22 x plus 3 minus 61. And that's it. So if you're entering this in your homework, you might also have to add the other side of the equals, which is your initial function. And at this point, you don't have to include the zeros if it's easier. So plus 4x plus 5. And, you know, a little history on the equal sign. These two functions, or these two sides of the equal sign, are the same. They are equal. So that's why we can use the equal sign. And that's how you use synthetic division to do the same thing as long division. So, and of course you can check your work. Let's see here. So here we've got our next example. I'm going to cover up the answers. We've got our quotient divided by, well, this is our divisor. I gotta get better at these vocabulary words. So we're gonna set up our synthetic division, and it does say write your answer in that weird form. It's not weird, but I don't know, it's strange to me, but that's fine. So using the coefficients again, so here we look at our divisor, or we first look at our divisor for this number right here. So which number is going to make that equal to 4? If I write out all the steps, equal to 0, so then x is going to equal 4. So that's what we put there. So then we're going to go through our coefficients. This is already written in standard form, and we're just going to go down the line. So that's 2, 1, negative 35. There is no x to the first, so we're going to put a 0 there, and then a minus 7. So then, to get these numbers, this is going to come straight down. 2 times 4 is 8. Add it together. So 9 times 4 is 36. Add it together. You get 1. 1 times 4 is 4. Add it together. You get 4. 4 times 4 is 16. Add it together. You get 9. So remember, this is going to be our remainder. This is going to be our answer, if you will. So let's see what they got. Oh, look, it's flashcards. Where are A, P of A, and the coefficients of the quotient represented in synthetic division? So A is the first value in the top row placed within the box. Boop. P of A is the last value in the bottom, aka the remainder. And the coefficients, boop, right there. Oh, I'm sorry, they're asking about the answer, the final coefficients. That's right there. I don't want to steer you wrong. So using the results of synthetic division, and here is the answer that we got. So notice how it lines up with this right there. We've got our remainder, our coefficients, and then our divisor. Too easy, right? So why is the degree of quotients 3 and not 4? Because we factored out 1 right there. That's what I would say. So to check your work, you can always check your work just multiply everything out and then combine like terms, you should get your original equation right there. If you don't, either your math here is wrong or you did something wrong earlier. Why does the check step confirm that work is correct? The resulting product plus the remainder is the same as the original polynomial. Does long division produce the same result as synthetic division? Yes, or I wouldn't be spending time teaching it to you. All right, next up, we can use synthetic division to find factors of a polynomial. So this is the same as using long division, and if you get a remainder of 0, it is a factor. So in the same way, synthetic division can determine whether x minus a is a factor of p of x, or some polynomial function. So factor theorem, the remainder is 0 when a polynomial p of x is divided by x minus a if and only if x minus a is a factor of p of x. So what that's saying is x minus a is a factor of p of x if, when you divide it all out, you do not have a remainder. And that should hopefully make sense. Because that's, I don't know how the numbers work. So, there's that. So let's try it out. So it says, determine whether the binomial x plus 7 is a factor of p of x, and they give us an equation. If it is, identify any other binomial factors of p of x. So, first of all, we need to find the zeros for that, or if you just use your theorem, since it says x minus a, it's always going to be the opposite sign of that. I like to remember the zeros. I don't know why that sticks in my brain more, but again, either way. So x in this case is going to be negative 7, because that's what's going to make this equal to 0. And then we just go through. We've got a 1, 8, 5, and negative 14. So here we go. Here's our negative 7. And we have our 1, 8, 5, and negative 14. So the 1 comes down. 1 times negative 7 is negative 7. Then we add. And then we get 1. 1 times negative 7 is negative 7. And then we add, going down. Then we get negative 2. 2 times negative 7 is 14. And then we add, going down. And then we get 0. So because that is 0, that means that our remainder is 0, which means that x plus 7 is in fact a factor of this polynomial. So let's make sure that that's what they got. Oh, they're testing me on my vocabulary. Here I go. The divisor of the problem is, that's the x plus 7, right? Okay. The factor theorem requires that p of x be divided by x minus a. If x minus a equals x plus 7, then a must equal negative 7. Whew. Got it. Since the remainder is 0, x plus 7 is a factor of p of x. Done. What is the justification for this statement? Do they have the theorem listed here? The factor theorem. It's the theorem they gave us up here. By the way, theorems are basically mathematical laws that always work. They usually have, like very specific requirements, but theorems you can think of as mathematical laws. They have been proven. There are proofs out there, and you just have to accept them as true. different than a definition. So if you guys remember I equals square root of -1, that's a definition. That is not a theorem. You can't prove that. We just had to come up with that. So we defined it like that. Anyway, so P of x can be written like this. We pull the factor out, and so now we have that polynomial remaining. So now we can factor the trinomial, this part right here. So we've got a -2. So then -2 or -1 plus 2 is going to give us our positive right here. So this is just a normal factoring problem at this point. So then we make it to that. So if x squared plus x minus 2 had not been factorable, which of the following would be factors of P of x? Select all that apply. I guess x plus 5. I'm sorry, x plus 7. That would be the only thing that it would be factorable by. You know, sometimes you just need to find closure, right? Polynomials feel the same way. So our next task is polynomials and closure. Closure? What is that? To be completely honest, I don't know. I haven't heard of closure until now. But polynomials and closure, so a set of numbers is said to have closure under a given operation if the result of the operation on any two numbers in the set is also in the set. You can extend this definition of closure to determine under which operations, if any, the set of the polynomial is closed. So before we go on, since I don't know if you've ever heard of closure before, but you can talk about a set of all real numbers. So that is our set. And our set is closed under addition. So if you take any two numbers in the real number line, so 2 plus 3, you are going to get another number in the real number line, is 5. So addition and subtraction are closed because you have a set in the real number line, and if you add or subtract, you're still going to get there. However, multiplication is closed, so you can think about that. You can take any numbers in the real number line, 6 times 1, 2, 3, 4, 7. I don't know, I just made up a number right there. But this is still a real number, and that's going to equal another real number. So addition, subtraction, and multiplication are all closed. Division is not always closed. So remember, the real number line, specifically, if you limit yourself to integers, all of a sudden, forgot the symbol for integers, but if you've got 2 divided by 3, those are on the real integer line, but they are not, but 2/3 is not on the integer line. So divided does not always have closure. It'll depend on the set of numbers that you're dealing with. Okay, so determine if the set of polynomials is closed under addition. So we're doing a little bit of theoretical math here. So you've got a P of x consisting of the sum of several monomial terms in the form a x of m, where a is a real number and m is a whole number. If a x to the mth power is a term in the polynomial P of x, and b x to the mth power is a term in the polynomial Q of x, then if you add them together, somewhere in there you're going to find a x to the power of m plus b x to the power of m, which you can then factor out your x to the m, and you have a plus b on the inside of there. So we come down here. So what is the missing entry in the step? A plus B. So this is kind of theoretical math, or this is the kind of math that you would use for proofs. Let's see here. So the set of real numbers is closed under addition. As a result, which of the following statements are true about the x to the mth term above? Select all that apply. The coefficient of x to the m must be a real number. I'll agree to that. The xm term must be a monomial by definition of a monomial. I think so, but I don't specifically remember the definition of a monomial. I know, I'm bad. I'm not good with vocabulary. The coefficient of x to the m must be a rational number? Not necessarily. It could be irrational, like pi or something like that. The x to the m term must be a monomial by the factor theorem. No, I don't agree with that at all. Good thinking. So complete the following statements. Every term of the sum p of x plus q of x is a monomial. So p of x plus is a, no, I take that back. Is a polynomial because of the, I don't know, definition of a polynomial. Oh. So this was probably a monomial. All that hard work and effort paid off. So the sum of the polynomials itself is a polynomial. What does this mean for the set of polynomials? Justify your answer. So it means that it is closed. So that's all that closure means. Hey, so that's our lesson. Try the check on learning. It's going to be good times, I'm sure, will be had by all. And if you need help, of course, check my next video. I'll see you in class.